Hi guys, this video shows the performance of the tomato sauce based on simple experiments that are affected by the microstructures and the rheologies. Tomato sauce is a two-phase colloidal system. The branch network microstructures are presented which are related to the rheology and flow properties, such as yield stress, shear thinning, and the disentropy. In tomato sauce, the different performances of temperature, dispensing, and spreading are affected by various parameters such as temperature, pressure, and yield stress. In this video, we are going to illustrate the link between product performances and microstructure by quantifying the temperature, pressure, and yield stress in various brands of tomato sauce includes the result analysis of microstructure changes. The first experiment showing the effects of various viscosity to the texture of tomato sauce under different temperatures.
In order to study the viscosity of tomato sauce, we prepared a three-defined ketchup. Firstly, thermometer was used to measure room temperature at 24 degrees, and then extracting 1 milliliter ketchup from injector and shipping them into specified round droplets on the whiteboard. The next step is to measure the time scale and length scale for 3 ketchup. When the whiteboard is placed vertically, we measure the falling length in each droplet within 80 seconds and collected all data. Our group also studied the effects of different temperature on the flow velocity of ketchup. Putting 3 cups of ketchup in water bath and heating by kitchen gas. Once temperature reached 45 degrees, stop heating and repeat the same operation, increasing temperature to 65 degrees. The flow velocity can also be measured. From the data graph, master food followed fastest and followed by fountain and hence at the same temperature. Besides, flow rate will increase with temperature for each ketchup.
From the experiment 1, it can be concluded that Heinz tomato had the largest viscosity than other two brands, and heating does affect the viscosity of tomato sauce. The tomato sauce slides further with the increasing of temperature. Each brand of tomato sauce shows the same trend that the viscosity is increasing. Also, microstructure is changed during the temperature raising, that the cohesion between molecular decreases and results the decrease of viscosity. As we discussed in last presentation, network structure is formed in tomato sauce, and the increasing in temperature destabilizes the network. Thus, the viscosity of all the tomato sauce goes down.
In the experiment 2, the temperature and volume are not changed. Then we use cones to provide subsequent stress. It is separated into 3 groups with different subsequent stress. Then we measure the time of flowing of different brands. So, we use 5 cones in the first test. As you can see, the fountain is the farthest one and the Heinz is the last one. In the test 2, we add another 5 cones. In this test, the time of fountain and master foods is almost the same. They were squeezed out easily, and Heinz is still slower than others. When we put 15 coins on them, the time range is sharply shortened. Although the Heinz is still the hardest one, it is much faster when the stretch is harder. So this test is actually a simulation of squeezing tomato sauce. When the stress is harder, they flows faster. So the tomato sauce is considered to be a shear-thin fluid. Heinz costs the longest time to flow out, so it is harder to be squeezed out. This is because the network structure in this brand is stronger, which gives the higher viscosity. However, once it is shared, the network structure will be broken and layered. Then it is very easy to squeeze out the tomato sauce.
Tomato sauce is non-Newtonian fluid and has shear thinning property. From the results, it can be seen that the falling time decreases with the increasing of pressure ended, and hence tomato sauce had the longest falling time. With the subsequent stress apply, microstructure changes and become loose. As shown in the 2 graphs, weak network structure and heterogeneous region are formed after shearing.
In the third experiment, we are continually focusing on the using stage. After squeezing it, maintaining the tomato sauce on food is another performance we need to consider. For example, if its flowing property is like water, it will flow into the holes on the bread and be absorbed. This will make the sourdough vetted and losing its crispy texture. Regarding this performance, we do the slump test to compare the different yield stress. The constant conditions are temperature and the volume at the beginning. Then remove the container and the fluid will slump but at a different level. The result of this sample test is obviously shown in these videos. That hints can maintain a relatively shape compared with another two. At the same time, this indicates its high yield stress. As a result, this type can keep the sourdough crispy before you eat it.
Further results is showing that after removing the container, Heinz tomato sauce spread less than other two brands, which indicate the biggest yield stress. Yield stress in tomato sauce is caused by the branched network structure, which results from attractive particle-to-particle interactions. And homogenization in manufacturing process will result different yield stress. The microstructure will be destabilized by over-homogenizations.
In conclusion, we can see the link between the performance of the tomato sauce and its microstructure. The performance of texture, dispensing, and spreading depend on the change of the temperature, pressure, and yield stress, which relates to the change in microstructures.